Hey everyone, and welcome back to the channel. Today, we're tackling LeetCode problem number 7, reverse integer. This is a classic problem often seen in coding interviews, and it's categorized as medium difficulty. The goal is simple. Given a 32-bit signed integer, we need to reverse its digits. For example, if the input is 123, the output should be 321. Sounds straightforward, right? But there are some tricky edge cases to consider. What if the input is negative? Or what if the reversed integer overflows the 32-bit signed integer range? We'll explore all these aspects today, so stick around. We'll not just solve the problem, we will analyze different approaches, understand their limitations, and finally arrive at an optimized solution. Get ready to level up your coding skills. Understanding with examples. Let's look at some examples to get a better grasp. If the input is 123, the reversed integer is 321. Simple enough. Now consider negative 123. The reversed integer should be negative 321. Notice that the negative sign is preserved. What about 120? The reversed integer is 12. The trailing zeros are dropped during the reversal. But here's where things get interesting. Suppose we have a large number like 15342364669. If we try to reverse this, we end up with 9646324351, which exceeds the 32-bit signed integer limit. This is a crucial constraint to handle. We'll need to account for potential overflow while designing our solution. This problem highlights the importance of carefully considering all edge cases before jumping into coding. Brute force approach. One way to approach this is through a brute force method. We can convert the integer to a string, reverse the string, and then convert it back to an integer. This is simple to understand, but it's not very efficient. It involves extra steps of conversion, which impacts performance, especially with larger numbers. Let's imagine we iterate through the digits, building the reverse number bit by bit. This will still have the problem of potential overflow without proper checks, making it inefficient and prone to errors for large numbers. We want a more efficient and robust approach for optimal performance and to avoid potential pitfalls like integer overflow. Optimal solution. The optimal solution involves a clever approach that avoids string conversion. We'll work directly with the integer. We'll use the modulo operator, % to extract the last digit, and integer division, W, to remove the last digit. We'll build the reversed integer step by step, carefully checking for potential overflow at each step. We will reverse the number digit by digit, building up the reversed number. Before adding each digit, we will check if adding it could cause an overflow. This approach is efficient and handles overflow gracefully, making it a superior solution to brute force methods. This dynamic approach ensures that we address the potential for overflow and maintain efficiency without string conversions. Code implementation. Let's see the code in Python. We'll start by defining a function called reverse integer. It takes an integer x as input. We'll initialize a variable, reverse num, to 0, and a variable sign to 1 if the number is positive and -1 otherwise. Then we enter a while loop that continues as long as x is not 0. Inside the loop, we extract the last digit using the modulo operator, and then check if adding it to the reverse num will cause overflow. If not, we append this digit and update x. Finally, we return the reverse num multiplied by the sign. This concise implementation efficiently handles both positive and negative, and, critically, it avoids overflow errors. Time and space complexity. The time complexity of this algorithm is O of n, where n is the number of digits in the input integer. This is because we iterate through the digits once. The space complexity is O of 1, because we only use a few constant extra variables. This makes it a very efficient solution compared to approaches with higher complexities, such as O of n squared. This algorithm's efficiency is evident in its linear time complexity and constant space usage, making it a clear choice for handling even very large numbers within the constraints of the problem. Engagement break. So, there you have it. We've successfully tackled the reverse integer problem. Before we wrap up, don't forget to smash that like button if you found this helpful. And if you're new here, subscribe to the channel for more LeetCode solutions and coding tutorials. Let me know in the comments what